So let's take a look at the evaluation of triple integrals in spherical coordinates. Let's find the volume of a sphere that has a radius of capital R. This means that our radial value will go from 0 to R. Angular value is free to roam from 0 to 2 pi. Our polar angle will be free to go from 0 to pi. If we are simply interested in the volume, we would set the function equal to 1. By Fubini's theorem, we are allowed to evaluate this in any order that we'd like. The only trick to remember is that we have this volume distortion factor. You can separate this into a product of three integrals using simple properties of partial integration. This will end up giving me a negative cosine phi from 0 to pi times a 2 pi. This will be a 1/3 r cubed. We'll get a negative cosine of pi, subtract cosine of 0, times 2 pi times 1/3 r cubed. Cosine of pi is -1. Subtract a 1, this gives me a -2. So at the end of the day, this gives me 4 pi over 3 r cubed, just like I expect. Very simple when we're in the right coordinate system. Very often, triple integrals are used just to evaluate volumes. As another example, let's find the volume of the region that's inside the sphere. X squared plus y squared plus z squared is 4. And also outside of the cone, z equals the square root of x squared plus y squared, above the xy plane. So the cone that we've got here has this type of shape. And then the sphere sits on top of it, above this xy plane. So you could think of it as having an inner wall and an outer wall. So there's the inner wall formed due to the cone. It will have this hole in the top. And essentially the volume that we're looking for is everything in there. The radial coordinate will go from 0 to 2, and we can see quite easily that our theta will go from 0 to 2 pi. We need to know what this phi value is that will generate the boundary of the cone. Another way to simplify this is to remember that the cone can be written like this. This is another way of writing this cylindrical R. From earlier, z is rho cosine of phi and r is rho sine of phi. That means we can set them equal to each other. Rho cos phi equals rho sine phi. The rho's will cancel. This will give us a tangent phi equals 1. In our case, this means that phi has to be pi over 4. Our polar limit now is bounded on the bottom by pi over 4, and then is free to go down to the xy plane. Phi is pi over 2. The volume of this region then becomes the following. 0 to 2 pi, 0 to 2, we'll have a rho squared sine phi, d rho, d theta, d phi. By Fubini's theorem, we can integrate this in any order we'd like. By properties of integration for partial integrals, we can also separate this, and we end up getting the following integral. This is going to be a negative cosine of phi from pi over 4 to pi over 2. This is going to give us a 2 pi. This will give us a 1/3 rho cubed evaluated from 0 to 2. We'll get a negative cosine of pi over 2 minus cosine of pi over 4 times a 2 pi times an 8 over 3. Cosine of pi over 2 is 0. This is 1 over root 2. This ends up giving us a 16 pi over 3 root 2 as the volume. Now, as our final example, we will try to find the volume of a cone that has a radius of capital R and a height of capital H. So we'll just talk about the top half of the cone here. This value right here is R, and we've got this value of H above. Now again, we've got our coordinate axes there, just as normal. How to describe this in spherical coordinates? The simplest thing we could say right now is that theta is going to have to go from 0 to 2 pi. But we're going to need to know what the polar angle is, and we're going to need to know what the radial limits are. From before, we can talk about the equation of a cone. Now, in Cartesian coordinates, it's usually x squared plus y squared square rooted. We're going to need this dial, this c, to ensure that we can get the right values for z and for r. So when we are at a height of h, we want to have a radius of r. So that means that c has to be h over r. So the equation of the cone will then be z is h over r times this little r. If we take a look at the side view of this cone, it will look like a triangle. Here's our r, there's our rho, and here's our angle. Z is always fixed at a constant height. Remember that z is cosine of phi, and so that means rho will be trapped at the top by h over the cosine of phi. Remember that from the equation of the cone, we've got that z is rho cosine of phi. We'll have an h over r is rho sine of phi. So what this is going to tell us is that the tangent of phi is r over h, and that means then that phi is going to be at some maximum value of inverse tangent of r over h. We'll now have an integral 0 to 2 pi in the azimuth angle. We'll have an integral from 0 to tan inverse of big R over h. And our radial limit will go from 0 to h over the cosine of phi. We'll have rho squared sine phi d rho d phi d theta. We have to be a little careful because this limit contains a phi. So we have to do the rho integral before we do the phi integral. So this will end up giving us a 0 to 2 pi, 0 to tan inverse of r over h. A sine phi, which is constant, will have a 1/3 rho cubed evaluated from 0 to h over the cosine of phi d phi d theta. 0 to 2 pi, 0 to tan inverse of r over h. We'll have our sine phi present, and now we'll get h over the cosine of phi cubed d phi d theta. This integral may look scary, but there are many things constant. We can take out the h over 3, and what we've now got is an integral of sine phi over cosine of phi cubed with respect to phi. This can be done very simply with the substitution. U is going to be cosine of phi, du is going to be negative sine of phi, d phi. When phi is 0, this tells us that u is the cosine of 0, which is 1. When phi is this tan inverse, u is the cosine of the tan inverse of r over h. Now that may seem worrisome, but follow the process. We will get an h cubed over 3. This theta integral will just produce a 2 pi integral from 1 to the cosine of the tan inverse of r over h, u to the minus 3 with a negative in our du. This will be 2 pi h cubed over 3. We'll have a negative sign, and this will give us u to the minus 2 over minus 2, evaluated from those two limits. Pi h cubed over 3, this negative and that negative will go away, this 2 and that 2 will go away. 1 over the cosine of this inverse tangent of r over h squared, subtract 1. This can be written as secant squared of this tan inverse of r over h, subtract 1. There's a trig identity that says 1 plus tan squared is secant squared. So this ends up being the tangent squared of the inverse tangent of r over h. Remember that this tangent square is on the outside, so we will have the tangent of an inverse tangent all squared, which just boils down to an r over h all squared. So at the end of the day, the volume here is pi big H cubed over 3 r squared over h squared, which is 1/3 pi r squared h as expected.